Lesson 1, Data Representation and Encodings. Welcome to our first lesson on computing fundamentals. Today we are exploring how computers represent different types of data. At the core is binary, where each digit carries a place value that doubles from right to left, like 1, 2, 4, and 8. To convert a binary number like 1101 to decimal, you simply add the place values where there is a 1, giving us 13. We also use hexadecimal, or base 16. In hex, the digit f equals 15 in decimal. Therefore, a hex value like 2f converts to 47, because 2 times 16 plus 15 equals 47. When dealing with negative integers, computers can use different methods. Sign and magnitude uses the most significant bit as the sign, where a 1 means negative, and the remaining bits store the magnitude. Alternatively, the widely used 2's complement method finds a negative value by inverting the binary bits of the positive number and adding 1. If you have an n-bit 2's complement number, the representable range is from -2 to the power of n-1 up to 2 to the power of n-1 minus 1. For encoding decimal digits directly, we use 8421 BCD, which represents each decimal digit from 0 to 9 as a 4-bit binary pattern. For instance, the decimal digit 4 is 0100, and 7 is 0111. Finally, for text, we have ASCII, a historically 7-bit character code for basic Latin letters and digits. In contrast, Unicode is a much larger universal encoding, designed to represent characters from essentially all writing systems.
Lesson 2, Logic Gates and Boolean Algebra. Let's dive into the logic circuits that make computation possible. Hardware relies on logic gates. An AND gate outputs a 1 exclusively when every input is a 1. An XOR gate outputs a 1 only when its inputs differ. If both inputs are 1, the XOR output is 0. Interestingly, NAND and NOR gates are known as universal gates because any combinational logic function can be implemented using only NAND gates or only NOR gates. To simplify these logic circuits, we use Boolean algebra. Important rules include De Morgan's law, which shows that the complement of a sum is the product of the complements. There is also the absorption law, which states that x plus x and y simply equals x. When a Boolean expression evaluates to true for every possible input combination, we call it a tautology. We also design special circuits called adders to perform arithmetic. A half adder adds 2 bits without a carry in, calculating the sum with an XOR operation and the carry with an AND operation. A full adder differs from a half adder because it includes a carry in input in addition to the 2 operand bits, producing both a sum and a carry out so that multi-bit adders can be cascaded. Finally, engineers visually simplify Boolean expressions using Carnot maps. If you are working with a 3-variable Carnot map, which has 8 cells, remember that valid single groups of 1 cells must always contain a power of 2, specifically 1, 2, 4, or 8 adjacent cells.
Lesson 3, Computer Architecture and Memory. In this lesson, we will look at computer architecture and memory systems. In the von Neumann architecture, both programs and data share the same memory space and are accessed by the CPU over shared pathways. Communication between these components happens via buses. The address bus is specifically responsible for carrying the location of the memory cell or input-output port being accessed. Inside the CPU, processing follows the fetch, decode, execute cycle. During the fetch stage, a special register called the instruction pointer, or program counter, holds the address of the very next instruction. This address is then copied to the memory address register, or MAR. The role of the MAR is to hold the exact memory address currently being read from or written to. When we look at memory types, there is a clear contrast between SRAM and DRAM. SRAM is faster and is typically used for cache memory. The main purpose of cache is to hold frequently used instructions and data close to the CPU for faster access. DRAM, meanwhile, is denser and used for main memory. For firmware, computers often use EEPROM, a specific type of read-only memory that can be electrically erased and reprogrammed. Finally, when it comes to mass storage, Media like magnetic tape stores data linearly. Because reaching a specific record requires passing earlier ones, magnetic tape is best classified as serial or sequential access storage. Lesson 4. Assembly Language and System Software. Let's wrap up by exploring assembly language and system software. System software is the layer that manages hardware and provides services for applications, including operating systems and translators. Programmers write source code with mnemonics. An instruction comprises an opcode and 0 or more operands. The opcode represents the specific operation to perform, such as MOV or ADD. Assembly instructions use different addressing modes. Immediate addressing places a constant directly into a register, like moving the immediate hex value 000F into register AX. Direct addressing, however, specifies a memory address, for example, moving the contents of memory location 2000 hex into register BX. Other common instructions include SUB, which performs subtraction, like subtracting BX from AX, and INC, which increments its operand by 1. For decision-making, the CMP instruction compares two values. After a comparison, an instruction like JG will trigger a jump if the first operand is greater than the second. Assembly also heavily relies on the stack structure via the stack pointer. The push instruction places a value on the stack, while pop removes it. To execute assembly, an assembler must translate the human-readable source code into object code, which is the machine-oriented output used before linking. Programs are also translated using compilers and interpreters. The key difference is that a compiler translates the whole source program into object or machine code before running, whereas an interpreter translates and executes the source statement by statement.
Thanks for watching. For free practice questions, study guides, and flashcards, visit exampreprise.com. Good luck on your exam!